Welcome to Chapter 5, the final chapter of the Deep Learning Fundamentals series. In this lecture, we bring everything together by building a complete deep learning project from scratch. We will train a neural network to classify handwritten digits using the MNIST dataset. You will see how all the concepts from previous chapters, including neural network architecture, forward propagation, backpropagation, and optimization, come together in a real working system. The MNIST dataset is one of the most widely used benchmarks in machine learning. It consists of 60,000 training images and 10,000 test images of handwritten digits from 0 through 9, giving us 10 classes. Each image is 28 by 28 pixels in grayscale, meaning each pixel has a single intensity value rather than RGB channels. When we flatten a 28 by 28 image, we get a vector of 784 values, which becomes the input to our neural network. MNIST is an excellent starting point because it is small enough to train quickly, yet complex enough to demonstrate real deep learning concepts. Before feeding images into our network, we need proper preprocessing. PyTorch provides the to-tensor transform, which converts an image into a tensor and automatically scales pixel values from the original range of 0 to 255 down to a range of 0 to 1. We then apply a normalized transform, which standardizes the data using a specified mean and standard deviation, centering the distribution around 0. This normalization helps the network learn more efficiently by ensuring consistent input scales. The data loader wraps our dataset and handles batching with a batch size of 64, shuffling for training to prevent the model from learning the order of examples, and parallel data loading with 2 worker processes to keep the GPU fed with data. Our MNIST classifier is a fully connected neural network with 4 layers. The input layer takes 784 features, which is the flattened 28 by 28 image, and maps them to 256 neurons. The second hidden layer goes from 256 to 128 neurons, and the third from 128 to 64. Finally, the output layer maps from 64 neurons to 10 classes, 1 for each digit. Between each layer, we apply RayLU activation to introduce nonlinearity, batch normalization to stabilize training by normalizing activations within each mini-batch, and dropout to randomly deactivate neurons during training, which prevents overfitting. This architecture progressively compresses the representation, forcing the network to learn the most important features. The training pipeline ties together 3 key components. First, we use cross-entropy loss as our loss function, which combines log softmax and negative log likelihood and is ideal for multi-class classification problems. Second, we use the Atom optimizer with a learning rate of 0.001. Atom adapts the learning rate for each parameter individually, combining the benefits of momentum and RMS prop that we covered in the optimization chapter. Third, we add a reduce-on-plateau learning rate scheduler, which monitors the validation loss and reduces the learning rate when improvement stalls. This prevents the model from overshooting minima in later training stages. Let us walk through what happens in each training iteration. First, we iterate over epochs, where each epoch processes the entire training set once. Within each epoch, we loop over mini-batches from the data loader. For each batch, we perform the forward pass, feeding input through the network to get predictions. Then we compute the loss by comparing predictions to true labels using cross-entropy loss. Next comes the backward pass, where we call the backward method on the loss to compute gradients for every parameter via backpropagation. Finally, the optimizer updates the weights using these gradients. We must remember to zero the gradients before each backward pass, otherwise PyTorch accumulates gradients across iterations. After each epoch, we evaluate on the validation set to monitor for overfitting. Accuracy alone is not sufficient to fully evaluate a classifier. We need several complementary metrics. Precision measures how many of our positive predictions were actually correct, calculated as true positives divided by true positives plus false positives. Recall measures how many actual positives we successfully identified, calculated as true positives divided by true positives plus false negatives. The F1 score is the harmonic mean of precision and recall, providing a single balanced metric. The confusion matrix gives us the complete picture, showing predictions versus actual labels in a grid format, making it easy to spot which digit pairs the model confuses most often. For example, digits 3 and 8, or 4 and 9, are commonly confused due to visual similarity. Hyperparameter tuning is the process of finding the best configuration for your model. Grid search is a systematic approach where we define a set of values for each hyperparameter and try every combination. Key hyperparameters to tune include the learning rate, trying values like 0.01, 0.001, and 0.0001, the batch size, experimenting with 32, 64, and 128, and the network architecture itself, testing different layer widths and depths. For each combination, we train the model and evaluate on the validation set, not the test set, to avoid data leakage. We track all results and select the configuration with the best validation performance. While grid search is exhaustive, more advanced methods like random search and Bayesian optimization can explore the space more efficiently. Let us now see the entire project workflow from start to finish. We begin by loading and preprocessing the MNIST data with appropriate transforms. We define our model architecture with the layer sizes and regularization techniques we discussed. We set up the loss function, optimizer, and learning rate scheduler. Then we run the training loop for a set number of epochs, monitoring both training and validation metrics. After training completes, we evaluate on the held-out test set to get our final performance numbers. A well-tuned model on MNIST can achieve over 98% accuracy. The complete pipeline, from raw data to trained model, demonstrates every concept we have covered across this entire series. Congratulations on completing the entire Deep Learning Fundamentals series. Let us recap what we covered across all 5 chapters. In Chapter 1, we learned the foundations of neural networks, including neurons, layers, and activation functions. Chapter 2 covered the forward pass, showing how data flows through a network to produce predictions. In Chapter 3, we explored backpropagation, the algorithm that computes gradients for learning. Chapter 3 introduced gradient descent, mini-batch training and momentum, and Chapter 4 added regularization together with adaptive optimizers like ATOM and learning rate scheduling. And here in Chapter 5, we brought it all together in a practical MNIST classification project. You now have a solid foundation in deep learning. For your next steps, consider exploring convolutional neural networks, or CNNs, which excel at image recognition by leveraging spatial structure. Then look into recurrent neural networks, or RNNs, designed for sequential data like text and time series. Finally, explore transformers, the architecture powering modern large language models. Thank you for learning with us, and best of luck on your deep learning journey.